This is from chapter 6 on the math 1324. Okay, so these are the topics that I will cover today. Systems of two linear equations and two variables, which is, I believe, is section 6.1, has the determine whether an ordered pair is a solution of a system of equations, graphing method. The graphing method is not covered in the 1324, but I'm going to show it anyway because there's different ways to solve systems of equations, and graphing is one of them. Then substitution, the elimination method, and then how do we apply matrices in real life? And then larger systems of equations, the elimination method, matrix method, and applications problems with three variables, and then at the end, matrix operations, adding, subtracting, and multiplying. Okay, so let's begin with the first topic, which is determine whether a solution, determine whether the given order list of numbers is a solution to the systems of equations. So for example, number one, you have two equations, right? Equation 1 and equation 2. So in order for this to be a solution, the point -1, 3 has to make both equations true. So for example, the -1 is the x value and the 3 is a y value. So I'm going to plug them in to both equations, right? So my x is -1 and my y is 3. So once I plug them in, right, then we simplify, so we get 1 equals to 1. So since this is true, then I get to proceed to number 2. But if it was false, I would have stopped there and say, you know what, this is not a solution. But since it's true for the first equation, I'll continue with the second one. So repeat the process. So I'm going to plug in -1 for x and 3 for y. It's going to give us 3 plus 6, which will give us 9. So 9 equals 9. So this is a solution to both equations. Since the order pair -1, 3 makes both equations true, then the order pair is a solution. Now let's try number 2. Again, we do the same process as number 1, but instead of -1 and 3, we're going to plug in 2 and -5. 2 and -0.5. So let's first start with equation 1. So my x is 2 and my y is -0.5. Right, so we get 1 minus 4. So -3 equals -3. So this is true, right? So then we proceed to the second equation. And we plug in 2 for x and -0.5 for y. This gives us 2 minus 2.5. Eventually, -0.5 does not equal to -5. So this is not true, which means that the order pair 2 -0.5 does not make both equations true. Then the order pair is not a solution. So number 1, it was a solution, and number 2, it wasn't. That's how you can check your work when you solve it by graphing, substitution, and by elimination methods. Now let's do the graphing method. For the graphing method on A, that means that you're going to have a solution, one solution. Okay. For example, if you're solving for x or for y and you get a number, right? You get an answer, that means you're going to get one solution. Example, say you get something like x equals 3 or y equals -2. That means we're going to get a solution. On B, on B, right, it's going to be a line on top of another line, which means there's going to be infinite solutions. So that's going to look something like this. A equals A, which means that you don't have no x's nor y's. They both got eliminated, but what's left, it actually is true. For example, 3 equals 3 or 0 equals 0. This means it's going to be infinite solutions. You see, I repeat, there was no x or y. And I know maybe some of you guys are confused at this time, but I will clarify it once we do some examples. And here on C, there's no solution. Why? Because the lines never intersect. So for example, you're going to get something like 3 equals 4, which will be no solution. But why? Because 3 does not equal 4. And the same thing as a 1 on B, you don't have no x or y's. They're both canceled. Okay, but you're going to have two numbers on opposite sides of the equal sign that are not the same. Okay, and that means no solution. Now, let's do example number 3, the graphing method. solve the system by graphing. So by graphing, right, so we learned how to graph, I believe, in chapter 1, which we got the slope and we got the b, which is the y-intercept. And the b, the y-intercept, is my starting point. So I'm going to start at 0, -6, which is down here at the bottom. Right? And then my slope is positive 3 over 1, which means I'm going to go up 3, 1, 2, 3, and 1 to the right. And then we connect the 2 points. That's my line for equation 1. Now for equation 2, it's not in proper form, right? So we have to put it in slope-intercept form to find my slope and my y-intercept. So let's put it in proper form. We're going to subtract. We're going to add 5x to both sides. We'll get negative 2y equals to 5x minus 10. Then we divide both sides by negative 2. So this is the equation in slope-intercept form. So my slope is negative 5 over 2, and my b is 5, and my y-intercept is 0, 5, which is my starting point. So I'm going to start at 0, 5. Then since my slope is negative 5 over 2, I'm going to go down 5 and 2 to the right. So let's start at 0, 5. I'm going to go down 5, 1, 2, 3, 4, 5, and 2 to the right, 1, 2. And then connect my 2 points. So this is my solution. Where they both intersect, the point will be 2, 0. That's my solution. That's how you solve systems of equations by graphing. You have to graph both lines, and where they intersect, that'll be your solution. Okay. Okay, now let's do it by substitution. You see, we have the very same linear system, but now we're going to do it another way, which is called by substitution. So by substitution, right, the objective here, or the object, is to try to have one of the variables isolated. In this case, on equation 1, the y is already by itself or isolated. So I'm going to use equation 1, right, the y value, which is 3x minus 6, and plug it into number 2. Okay, so I'm going to substitute 3x minus 6 for y. Now I'm going to distribute. So this becomes negative 5x minus 6x, and then negative 2 times negative 6 will give us positive 12. Going to combine like terms. So negative 5x minus 6 will give us negative 11x plus 12 equals negative 10. Now we have to solve for x. So we're going to subtract 12 to both sides, from both sides. So we get negative 11x equals to negative 22. Now we divide both sides by negative 11. So we get x equals to 2. Now we need to go back and plug in 2 for the x, another equation 1 or 2, whatever is easier for you. In my opinion, what's easier is equation 1. Why? Because we already have the y isolated. So all we do is we're going to plug in 2 for the x and simplify. So we're going to plug it in there. So 3 times 2 is 6. 6 minus 6 is 0. So my point is 2, 0. That's my solution. Okay, so this is called the substitution method. Consistent and dependent system means that there's going to be one solution. Okay. Okay, now let's do the very same problem, but let's do it by the elimination method. Okay, I know that I'm only doing one example of each one, but I think for the elimination method, I'm going to do a few more, because that's the one that you use when you're solving larger systems of equations. Okay, but now, in order to apply the elimination method, they both have to be in the ax plus by equals c form. For example, equation 1 is not in that form. So I need to rewrite it in proper form. So here I'm going to subtract 3x from both sides. So I have negative 3x plus y equals to negative 6. Now it's in proper form. So by the elimination method, you decide which one you want to eliminate, the x's or the y's, whatever is easier. In my opinion, it's easier to eliminate the y's. Why? Because we only have to multiply one equation by a number, right? So in this case, we're going to multiply equation 1 by 2. Why 2? Because if we want to get rid of the y's, right, we have to, if equation 2 is negative 2y, then the equation 1 has to be 2y. So I'm going to multiply 2 times every term on equation 1. So 2 times negative 3x will give us negative 6x. 2 times y will give us positive 2y. And 2 times negative 6 will give us negative 12. So equation 2, we'll just bring it over. Then we add them, right? That's why it's called the elimination method, because the y's got eliminated. So we got negative 11x equals negative 22. We divide both sides by negative 11, and we get x equals to 2. Now, like in the substitution form, we go back and plug in 2 for x in either equations 1 or 2. Whatever is easier. And in similar manner, equation 1 is easier because the y is already isolated. So I'm going to plug in 2 for the x's. So 6 minus 6 will give us 0. So my solution is 2, 0. Okay, now let's do the very same one, but instead of eliminating the y's, let's eliminate the x's, just so you find out that it's a little bit more work to get rid of the x's. Okay, so I'm going to repeat the same process as before, as the previous slide. So let me just go kind of quick here and get to that point. So here we go. Okay, remember in the last slide we got rid of the y's, but let's say you want to get rid of the x's. Okay, so then since they both are negative, right, and we want to eliminate the x's, I need to multiply 1 by a negative. So for example, equation 1, we're going to multiply by negative 5, and equation 2 by 3. So negative 5 times negative 3 will give us 15x, negative 5 times y will give us negative 5y, and negative 5 times negative 6 will give us 30. We're going to multiply equation 2 by 3. Again, why 3? Because 3 times negative 5 will give us negative 15x, and they'll be able to eliminate them. You see, so we get negative 11y equals to 0. We divide both sides by negative 11. So we get y equals to 0. Okay, now we go back to either equation 1 or 2, right? But we're going to plug in 0 for y. What's easier? I believe equation 2 will be easier. Why? Because here, if we put on equation 1 and we put 0, it's a little bit more work. If we put it on equation 2, it'll be a little bit less work. So it all depends on the student, what's easier for him or for her. Okay, but this is my opinion that it'll be easier to go in equation 2. So I'm going to plug in 0 for y. So we get negative 5x equals to negative 10. We divide both sides by negative 5. So the answer will be 2. So what's my answer? 2, 0. If you notice, I did it in 3 ways. By graphing, we got the same answer as substitution and the elimination method. For the elimination method, we did it both ways, right? We first got rid of the y's, right? And we got the same answer. And then the second, which is right now on this slide, we got rid of the x's. You see, guys, it's whatever is easier for the student. Okay, so I'm trying to show you different ways because we all think different as students, and but I will always try to tell you what's the easiest way. Okay, now solve the system by elimination. So here, right, equation 1 or 2. So here it doesn't matter what we're going to get rid of because both you need to multiply by negative 2. Why? Because if we want to get rid of the x's, negative 2 times 3 times 3x will give us negative 6x, and this way the x's will be eliminated. So let's multiply every term on equation 1 by negative 2. It's going to give us negative 6x plus 4y equals to negative 8. Then when we add them, we're going to get 0 equals 0. Remember when I had those two graphs, when they showed 2 lines intersecting, when they showed a line on top of a line, and I said when you have the same coefficients or numbers on both sides of the equal sign, and there's no x or y's, but this is true, then it's going to be infinite solutions. Here's a case of infinite solutions. And again, and it's called consistent dependent system. This notation here, mostly they use it in pre-cal 1, which is a math 13-14. Okay, but consistent dependent means that this is consistent because you have a solution, and the y depends on the x. I mean, the x depends on the y and vice versa. That's what it's called, consistent dependent, or the y depends on the x. Okay. Okay. Now we have something similar here. Okay, but now we can also do it by the elimination method. What I mean by similar is that once we get rid of what the x's and the y's, we're going to get something with no x or y's. For example, here we're going to get rid of the, say, the x's again, just multiply by -3. Right? So if we do that, we're going to get 0 equals to a number, right? So again, it was similar to number 6, example 6, but here, guys, this is not true. 0 does not equal -6. That means that these lines never intersect. As a matter of fact, they're called parallel lines. That means no solution. Okay, and this is called inconsistent system because there's no solution. Okay, now this is how this applies to a real life situation. Okay, for example, this is number 8. A 200-seat theater charges $8 for adults and $5 for children. If all seats were filled and the total ticket income was $1,435, how many adults and how many children were in the audience? Okay, now what's the solution here, guys? We need to find two equations. Okay, like I tell my students, we're going to use people with people and money with money, or seats with seats and money with money. What does that mean? It means that, for example, we're going to let x equal to adults and 5 equal to children's seats. And there's a total of 200 seats. So adult seats plus children's seats must equal to 200. So since x represents adults and y represents children, it's going to be x plus y equals to 200. Now let's do money with money. Okay? Here's how I show my students how to do these type of problems. So money with money, right? So if $8 is for adults, right? And x represents adults, so this is going to be 8x. Since children's tickets are $5 and y represents children's seats, this will be 5y. And what was the total income? 1,435. So this will be 8x plus 5y equals to 1,435. So I got my equation 2. Let's put them together. And now we can do them any way we want to, right? But the easiest way is by the elimination method. So here, what should we get rid of? The x's or the y's? It doesn't matter, right? Because both are about the same. I believe I'm going to get rid of the x's. So to get rid of the x's, I need to multiply equation 1 by -8. So after I distribute -8 times every term in equation 1, it gives us -8x minus 8y equals to -1600. Equation 2, we just bring it over. Right? So after we add them, the x's get eliminated, and we get -3y equals to -165. Then we divide both sides by -3. We get y equals to 55. Now I need to solve for x. So again, whatever is easier, and again, it's kind of obvious that equation 1 is easier. So let's go to equation 1. So we know that y equals 55. So let's plug them in. Let's plug it in for y. Then we subtract 55 from both sides. So we get x equals to 145 because 200 minus 55 gives us 145. So I got my x and my y, right? My x is 145, but y is 55, but that's not what they're asking for. They're asking how many adults and how many children were in the audience. So that's why here we have to, since x equals to adults, there's going to be 145 adult seats and 55 children seats. Okay, that's how you work problems into linear systems of equations. Okay, now let's do larger systems of linear equations. So in this case, we can have three lines, right? and with three variables, the x, y, and z. Okay, so to start off, it's always wise to have the coefficient on 1, right, on equation 1. So if you want, you can swap them at the beginning. So in this case, I'm going to rearrange it. I'm going to put equation 2, put it on 1, and bring equation 1 to 2. You see, I just switched them. Okay, now, there's got to be some kind of plan. Okay, like I tell my students in class this week, I told them that the plan is I'm going to get equation 1 and equation 2 and equations 1 and 3 and get rid of the x's, eliminate the x's. After I do that, I'm going to get a new equation 2 and a new equation 3. So I'm going to get the new equations 2 and 3, and I'm going to get rid of the y's or eliminate the y's. Then I'll be left with something like z equals to c, which c is a real number, which means z will be a number, equals to a number. Okay? After all these steps, the equation should look like something like this, right? You see, there's my first equation, and this is my second equation and my third equation. Then we're going to back substitute. Okay, so let me show you how it's done. Okay, here we go. So this is my linear system of equations. So I'm going to get 1 and 2 and get rid of the x's. So I'm going to multiply equation 1 by negative 2. So after I do that, I get negative 2x plus 6y minus 4z equals to 0. Equation 2, we just bring it over and then we add them. So if you notice, the x's will get eliminated. So I'm left with 4y minus 3z equals to 3. And that's my new equation 2. Now, I get equations 1 and 3 and also get rid of the x's. So I'm going to multiply equation 1 by negative 3. Because this is the reason why you always want to have something with 1x on equation 1, because it'll be easier to do the math. Okay? You see, for example, here all we do is multiply some number times equation 1, right, to get rid of the x's on equations 2 and 3. So in this case, the number that we chose was negative 3. Why? Because negative 3 times x will give us negative 3x. Then when added to equation 3, to the 3x, they'll be eliminated. Okay, so we get 10y minus 7z equals to 7. That's my new equation 3. Now we get equation 2, the new equation 2, the new equation 3, and we're going to get rid of the y's. A lot of, I mean, at times the book and also some instructors, they always say they want you to think about certain ways to eliminate them, right? But if you follow these steps, you can never go wrong. Just do equations 1 and 2 and 1 and 3, get rid of the x's. And then you're going to get 2 new equations and get rid of the y's. Because this way, you always have the steps in the foundation on how to solve for them. And then if once you know it by heart, then you can start doing other things. Okay, but for now, just keep it simple like this. Okay, now here, guys, I'm going to multiply equation 1 by negative 10 and equation 2 by 4. I know that the least common multiple of both is going to be 20, right? Because 4 goes into 20 and so does 10. But to me, that's some students, they don't know that 20 is the least common multiple of both. That's why I always tell them to multiply one equation by the other, right? Using the coefficients on both. For example, on equation 1, I'm going to use the coefficient from equation 2 for the y. And in equation 2, I'm going to use the coefficient on equation 1, but since they're both positive, I have to multiply 1 by a negative. So I decided to multiply equation 2 by negative 10 and equation 3 by 4. And here's my work. Right, so after you add them, the y's get eliminated, and then here we can solve for z. We divide both sides by 2, so z equals to negative 1. You see, guys, this is what we had on the previous slide, right? We always try to keep the first equation, right? For equation number 2, I can use the new equation 2 or the new equation 3. But I believe the new equation 2 is easier because those numbers are smaller. That's why I chose that one. But if you would have chosen 10y minus 7z equals to 7, you still get the same solutions. Okay, now I back substitute. So since I already know what my z is, which is -1, I'm going to go to equation 2, and I'm going to plug in -1 for z. And that way I can actually solve for y. So here in this case, we get 4y plus 3 equals 3. We subtract 3 from both sides. So we get 4y equals to 0. We divide by 4. So the answer is 0. So y is 0. So I already found the values for y and for z. Y, which is 0, -1. Now I go to equation 1, and I'm going to plug in the values for 0 for y and -1 for z, and solve for x. Okay, so in this case, we get x minus 2 equals 0. So x equals to 2. So I solve the linear system of the equations. I get x equals 0, x equals 2, y equals 0, and z equals -1. This is my actual point. Okay, now this method, the Gauss-Jordan method, it's a little bit challenging, but since this method will be used actually for people going for math engineering for students, but also you see the Gauss-Jordan method for students taking the 1325 for computer programming, something like that. This is programming. That's why I also included in my in this PowerPoint here. Okay, I'm going to go through it like the concept, then I'm going to go through it briefly, and then we'll do an example together. So this is a linear system of equations, right? It's going to be x minus 3y plus 2z equals 0. I believe this is the one that I did earlier, on the previous slide. So I have to convert it to matrix form, to an augmented matrix. If you notice, that's my matrix, so I get only the coefficients of each row. See, so there will be 3, 1, -1, and 7. This is called augmented matrix. Now, the matrix solve will be in reduced, the RREF stands for reduced row echelon form, which means all the ones, all the diagonals will be ones, you see? And the rest zeros. And then here are my solutions. This can actually be plugged in the calculator, and this is what you see when you get the answer. But I tell my students, I show them how to use a calculator, but they have to show me all the work on the exams and also during class. Okay, now how in the world are we going to do this? Okay, I'm going to show you step by step. I call it the three-step plan. Most books and they use like 9 different matrices, and so does, I believe, so do some instructors. But this method is called the Gauss-Jordan method, but I modified it in three simple steps. I call it step 1, step 2, and step 3, and each step has at most 2 steps, A and B. Okay, let me show you how it works. Okay, this is my augmented matrix, right? I'm going to let all letters be real numbers. So this is the reduced row echelon form. It should be something like this. After it's done, right? Is 1. You see all the ones. All the from the diagonals are ones, and the rest are zeros. So the value that's here will be the value for x and for y and for z. Okay, now here's the 3 steps. So step 1. This is row 1, row 2, and row 3. Step 1. I'm going to make these 2 zeros here. The e and the I must be zeros. So row 2 is going to change, and row 3 is going to change because the e and the I must be zeros. So after I execute step 1, this is the way it should look. Something like that. Now step 2, right? The B and the Q must be 0. You see, that's why it's color coded to fit the matrix here on top. You see the first row, second column, and the third row, second column, they have to be zeros, the B and the Q. So after I execute that step, there's my zeros there. Now my third step, the U and the N must be zeros. So step 3, row 1 is going to change because the U must be a 0 and the N must be a 0. And simplify if possible as you do each step, which I'll explain as I go along when I do an actual example. Okay, now this is the method, the math notation, right? By letting all letters be real numbers. But at times, students, they don't like letters. For example, when I was in school, when I would see too many letters, I would get confused because there was X, there was Y, and now whole bunch of letters. That's why I explain it a different way. I mean, the concept here. I just put number signs. Number signs means there's a number there. Okay, again, I'm going to go kind of quick with this, but it's the same thing. But instead of letters, all we do is use numbers. I mean, the number sign. See, after step 1, after step 2, it should look like this. After step 3, it should look something like this. Okay, and you simplify the 3 steps. So now let's do 1 for practice. This is number 10. Okay. So if you put that in the calculator, this should be the answer, right? 2, 0, -1. But let's see what how it works. So this is row 1, row 2, and row 3. So step 1, we're going to keep row 1 how it is. Now the 2 and the 3 must be 0. So I'm going to change row 2. And I'm going to change row 3 because the 3 must be a 0. That's why I put it in blue, so it can match step 1. So now I'm going to use row 1, right? So I'm going to multiply -2 times row 1. Why -2? Because -2 times 1 will give me -2. Then when I add it to row 2, that 2 will be eliminated. In a similar fashion, I'm going to multiply -3 times row 1 and add it to row 3. And here's my work. -2 row 1 is equal to -2 times, right, this is my row 1, 1, -3, 2, and 0. So it's going to give us -2, 6, -4, and 0. The row 2, we'll just bring it over. Right, this is row 2, the 2, -2, 1, and 3, and then we add them. If you notice, we get a 0 there where the 2 should be. So that's my new row 2. Now here's the second step, or part B for step 1. -3 row 1 will give us -3, 9, -6, and 0. When we add it to row 3, the row 3 will just bring it over. It's going to be 3, 1, -1, and 7. After we add them, right, there'll be a 0 on that spot right there. So we get 0, 10, -7, 7. So that's my new row 3. On the next slide, I'm going to carry this over, and then we're going to do the step 2. Okay. Remember the objective, right? So step 2, the -3 and the 10 must be zeros after we execute step 2. So step 2, we're going to keep row 2 how it is. So the -3 must be a 0. Right, so step 1, so row 1's got to change. And the 10 has to be a 0. So that row's got to change. So I have to use row 2. Okay, so check this out. So I'm going to multiply 3 because there's already a negative and a positive, so I don't need to multiply 9 by a negative. So I got 4 here. So I'm going to multiply 3 row 2 times 4 row 1. And here I'm also going to multiply -10 times row 2 and 4 times row 3. And here's my work. 3 row 2. We're going to multiply 3 times everything in row 2 times every element. This is what we get. And then plus 4 row 1. We're going to multiply 4 times every element in row 1. So after we add them, right, we get 4, 0, -1, and 9. So that's my new row 1. Repeat the process for step 2, part B. We multiply -10 times row 2. So we get 0, -40, 30, -30. And then 4 times row 3. So we get 0 to -2. So here's where I mentioned, right, to simplify if possible as we go along. So this can be simplified. We can divide everything by 2, every term by 2. So this is what we get for my new row 3. Okay, now I'm going to go to the next slide and finish off step 3. Okay, so here we are. So step 3, we're going to keep row 3 how it is, and the -1 on row 1 must be a 0. So that row's got to change. And the -3 in row 2 is got to be a 0, so that row's got to change. So I'm going to use row 3. So if I add 1 plus -1, right, they'll cancel. So I'm going to put row 3 plus row 1. In this case, I need to multiply 3 times row 3 and add it to row 2, so the -3 spot will also be 0. And here's my work. Right, we just add them. So we get 4008. So this can also be simplified. So it's going to be, we divide everything by 4, so it's going to be 1002. That's my new row 1. And 3 row 3, right? For the second part, 3 times row 3 will give us 003 -3 plus row 2, we just bring it over. After we add them, it's going to give us 0400. And remember, this has to be a 1, so we divide everything by 4, so we get 0100. That's my new row 2. So there's my solution. 2, 0, -1. Okay, now let's do one together real quick. Okay, so we're gonna we keep row 1, so we're gonna change row 2 and row 3. So I'm gonna multiply -2 times row 1 and add it to row 2. And I'm gonna add row 1 plus row 3. And here's my work. Step 1, AB. So -2 row 1. So we're gonna multiply -2 times everything in row 1, which is -2, -4, 2, and -12. We're going to add it to row 2. So after I execute it, we get 0, -5, 5, -10. And again, we can simplify. We divide everything by -5, so we get 0, 1, -1, and 2. That's my new row 2. So here we're going to add row 1 plus row 3. We get 0, 1, 0, 1. That's my new row 3. Okay, now step 2. Step 2, the 2 in row 1 must be a 0, so that's going to change. And my 1 in row 3 must be a 0, so that's going to change. So I'm going to multiply -2 row 2 and add it to row 1. And here I'm going to multiply -1 times row 2 and add it to row 3. And here's my work. So -2 row 2 equals to -2 times every element in row 2, which is 0, 1, -1, and 2. So we get 0, -2, 2, and -4. We're going to add it to row 1. So row 1 is 1, 2, -1, and 6. After we add them, right, we get 1, 0, 1, 2. So that's my new row 1. So for the second step, we just multiply -1 times row 2, which the signs are going to switch. If we're multiplying by -1, we're going to add it to row 3. So after we add them, we get 0, 0, 1, -1. So that's my new row 3. Now we're done with step 1 and step 2. So now comes step 3. So for step 3, we're going to keep row 3. The one on row 1, which is the third column, that has to be a 0, so that's going to change. And also the -1 in row 2 has to be a 0, so that's going to change. So I'm going to use row 3. So I'm going to multiply -1 times row 3 and add it to row 1. And for these two, right, for row 2, we're just going to add row 3 plus row 2. And here's the work. -1 row 3 will be -1 times every element in row 3, which is 0, 0, 1, -1. And row 1, we just bring it over. So after I execute the operation, we get 1, 0, 0, 3. That's my new row 1. So for the second step in step 3 or step B, we're going to add row 3 plus row 2. So we get 0, 1, 0, 1. So that's my new row 2. So what's my solution? Will be 3, 1, -1. This is how you do the Gauss-Jordan elimination method. Okay, so let's move on. Now, how does it apply to to real life. We're going to get, this is a word problem that requires 3 equations, okay? So we need to find 3 equations. So the first 2 are kind of simple to find. Like I repeated on the last word problem that I did, we're going to do people with people and money with money. And then the last equation will be the last sentence here, or the second to last sentence. So since this is first, right, we're going to let x equals to adults, y equals to teenagers, and z equals to preteens. And there were 470 total. So this equation will be x plus y plus z equals to 570. Now let's do money with money, right? So since adults are $5, that's going to be 5x. Since teenagers cost $3 and y represents teenagers, so that's going to be 3y. Preteens is going to be $2, and since z represents preteens, that's going to be 2z. And the total receipt or revenue was 1,150. So then we're going to add 5x plus 3y plus 2z equals to 1950. So I already got equations 1 and 2, but we're missing 3. Okay? So now, how do we find equation 3? The last sentence here, well, second to last sentence, is where we find equation 3. 3/4 as many teenagers as preteens attended. Okay? So since teenagers is y and preteens is z, this is how you write it. Okay, now, this can be a little bit confusing, but like I tell my students, you write it how it sounds, and then you put the coefficient on the other side of the equal sign. Okay, let me show you how it's done. Okay, because today was a good example. A student came that she went for tutoring, and she said that the people that she went, they gave it to her in this form, something like this. And I told her that was wrong, and then she was saying no, they said it was like this. That's why I tell my students, write it how it sounds. Okay, check this out. Doesn't it sound like this? Like 3/4 teenagers, right? And since y is teenagers, we put 3/4 y equals to z. And then I tell them to actually, I call it flip it, but maybe that's a bad word to use, flip it. What I mean by that, instead of putting 3/4 with a y, you put it where the z is. And that's the correct way. It works every time. Okay? Okay, now. So I'm going to multiply everything by 4. And then I'm going to subtract 3z to both sides because I want to put it in the same form as the equation, as a linear system. So I found equation number 3. Okay, now you can solve it either way. You can solve it by the way I showed you earlier, guys, by using 1 and 2 and 1 and 3 and so forth, or by matrix. Here, guys, since it's almost time, I'm going to go kind of quick. Through it. Okay, I did it this way. Okay, but this you'll be able to look at your own time. Okay, but for the meantime, because I want to get to the operation on matrices, this should be the answer, guys, and you can actually stop it and work it, right? And back substitute, and this should be your answer, guys, right? You can follow this PowerPoint here and put it on pause and see what they did. But this is the answer here, guys. Okay? So you can try it, but here's the actual solutions here. Because like I said, I don't want to take too much of your time because this is supposed to be an hour workshop and I'm already down to 5 minutes more. So now I'm going to do the matrices. I'm gonna explain how to add, subtract, and multiply. Okay. Okay. Now for matrices, the uppercase of the alphabet represents a matrix, and the lowercase represent the entry. These are called the elements or the entries. Okay. For example, if that's matrix A, the smaller case A means that's an element. The 11 means that this is row 1, column 1. Row 1, column 2, and so forth. Okay? So again, you see this is the rows and the columns. This is called the position of an element. Okay, let me show you what I mean. A11 stands for, the 11 stands for position. Position is row 1, column 1. A14 stands for the position. 14 is row 1, column 4. Okay, now, so A23 stands for, the 23 stands for position is row 2, column 3. Now, let's do a self-check here. What's the position of the following elements? A13, it means, right, the first row, third column, which will be, the spot will be 3. A24, the 2 stands for the second row, and the 4 stands for column 4. This is a second row, column 4, 1, 2, 3, 4, so it's going to be 8. Now for the size of a matrix, the size has to be the rows times the columns, or rows by columns. So the rows are across and the columns are are vertical. So this, for example, this one here is a 2 by 4. Why? Because there's 2 rows and 4 columns. Example 2, determine the dimensions of the matrices. This one here on the far left is going to be a 3, right? Because we have 1, 2, 3 rows and 3 columns, so it'll be a 3 by 3. The one in the middle, we got 3 rows, 1, 2, 3, and 1 column, so that'll be a 3 by 1. The last one, we have 1 row and 3 columns, so that'll be a 1 by 3. Okay. Now on this one, right? So what's the order of the matrix or the size? We got 1, 2, 3, 4, so that'll be 4 rows and 1, 2, 2 columns, so that'll be a 4 by 2. Okay, now comes matrix operations. In order for you to be able to add and subtract them, they have to be the same size, right? I can put here, in order to add or subtract, the matrices must be the same size. So for example, I'm going to add the matrix A and B, right? So I have to write the same entries. For example, A11 plus B11, which means the first row, first column on matrix A plus the first row, first column on matrix B, and so forth. Okay? Until you get to the end. Okay, now the sum of the two M and N matrix, X and Y, is the M and N matrix, X plus Y, in which each element is the sum of the corresponding elements of X and Y. In other words, this is saying that the sum will be, after you add the same position on matrix A and B, right? That'll be the sum, right? Because we're going to add these. Let me show an example, because at times the example is easier than the definition. And that's also the same thing for the difference. Okay? Example. A is a 2 by 3, right? We have 2 rows and 3 columns. B is a 2 by 3. C is a 2 by 2. And D is a 2 by 2. So let's do A plus B. Right? So A plus B is going to be 1, right? 1 plus 8. Negative 3 plus 0. 2 plus 1. 2 plus negative 1. 2 plus 3. Negative 1 plus 4. Right? So, hey guys, this is just to show you the steps, right? But you can go straight from here, right? Just looking at matrix A and B to get the answer. For example, what's 1 plus 8 is going to be 9. Negative 3 plus 0 will give us negative 3. 2 plus 1 will give us 3. 9 plus negative 1 will give us 1. And 2 plus 3 will give us 5. And negative 1 plus 4 will give us 3. That's your solution. Now let's try C plus D. Right? So it'll be 5 plus 2. 1 plus negative 1. Negative 4 plus 9. 3 plus negative 7. So it's going to be 7, 0, 5, and negative 4. That's my solution of C plus D. How about A plus C? A plus C cannot be done. Why? Because the matrix are different sizes. This is a 2 by 3, and a 2 by 2, not the same size, so that it cannot be done. And also similar with subtraction. Subtraction, right, is the same thing as addition, but the only difference is we're going to be subtracting. This will be 1 minus 8, negative 3 minus 0, 2 minus 1, 2 minus negative 1, 2 minus 3, and negative 1 minus 4. So it's going to give us negative 7, negative 3, 1, 3, negative 1, negative 5. That's my solution. How about C minus D? So it'll be 5 minus 2, 1 minus negative 1, negative 4 minus 9, 3 minus negative 7. So it's going to give us 3, 2, negative 13, and positive 10. That's my solution. And similar as the previous slide, A minus D cannot be done. It's not possible. Why? Because the matrices are not the same size. These are 2 by 3, these are 2 by 2. Now this is called a scalar. For the scalar, right, say it says to find 6 times matrix X. It just means that I'm going to multiply 6 times every element in matrix X. So it's going to be 6 times 2, 6 times 0, 6 times 5, 6 times 4, 6 times negative 2, and 6 times negative 3. So we're going to get 12, 0, 30, 24, negative 12, and negative 18. That's your solution. Okay, now find negative x. Negative x is the same thing as negative 1, right, times matrix x. So like I tell my students that if you multiply by a negative, right, or negative x, all you do is switch the signs on the matrix. Because negative 1 times 2 will give us negative 2. Negative 1 times 0 will give us 0. Negative 1 times 5 will give us negative 5. Negative 1 times 4 will give us negative 4. Negative 1 times negative 2 will give us a positive 2. And negative 1 times negative 3 will give us a positive 3. What was the observation? All the signs switch from the regular matrix X, right? Because you multiply by negative 1, all the signs switch on every element. Now let's do example number 16. Example number 16, we have negative 4a, which means I'm going to multiply negative 4 times matrix A. Negative 4 times negative 2, right? Negative 4 times 0, negative 4 times 5, and negative 4 times 3. It's going to give us 8, 0, negative 20, and negative 12. Now let's do B, which is 5 times B. 5 times matrix B. Matrix B is 0, 2, 4, negative 6. So I'm going to multiply 5 times 0, 5 times 2, 5 times 4, and 5 times negative 6. So it's going to give us 0, 10, 20, negative 30. Now for part C, right, add them both. So I would use the work for negative 4a, right? It was found in A, which was 8, 0, negative 20, negative 12. And the work for 5 times B, matrix B, was done in part B, which will give us 0, 10, 20, negative 30. Now to add them, it's going to be 8 plus 0, 0 plus 10, negative 20 plus 20, and negative 12 plus negative 30. It's going to give us 8, 10, 0, and negative 42. That's my solution. Now, for the matrix product, for multiplying matrices. Multiplying matrices can only be done under the following circumstance or condition. When you put, say you put the size of matrix A and the size of matrix B, you put them right there next to each other, right? So the two in the middle must match. If they match, then it can be done. If they don't match, then it's not possible. And the solution will be an M times P matrix. Okay, for example, if the size of matrix A is a 2 by 3, then matrix B must be a 3 by something. 3 by whatever, it can be a 3 by 1, a 3 by 2, but the 2 in the middle must match. And the answer will be a 2 by, whatever the number is here. Okay, now, given the following matrices, state whether the matrices can be multiplied. Okay, this is matrix B. Okay, matrix A is 2 by 3. Matrix B is a 2 by 2. And matrix C is a 3 by 2. Now, can we multiply A times B? Right, A times B cannot be done. Why? Because A is a 2 by 3 and B is a 2 by 2. You see the 2 in the middle numbers, digits cannot, you see they're not the same. So no, it cannot be done. Cannot be multiplied. How about B times A, right? Matrix B is a 2 by 2 and matrix A is a 2 by 3. Since the 2 in the middle match, right? So yes, it can be done. So, and the answer will be a 2 by 3. Matrix, the size will be a 2 by 3. How about A times C? We have a 2 by 3 for matrix A, and C is a 3 by 2. Yes, it can also be done, and the answer will be a 2 by 2 matrix. Okay, let's do some. So number 18, multiply the following. You have matrix A is 2, 4, 2, 0, 5, 4, negative 2, negative 3. It's a 2 by 3, right? And matrix B is a 2 by 2. So this is the way the book explains it. So let me show you how the book explains it, right? So it can be done. So step 1, I need to multiply the row on matrix B times every column on matrix A. So example, 1 times 2 will give us a 2. 0 times 4, right? So it's going to be 1 plus 0. So the answer is, 2 plus 0. So the answer is 2. Now step 2. For step 2, right? It's going to be the same row, but now I'm going to multiply it times the second column. Right? You see, on step 1, it was the first column. Step 2 will be the second column, and step 3 will be the third column. So it'll be 1 times 0 plus 0 times negative 2. The answer will be 0 plus 0. The answer will be 0. So that goes on the first row, second column. Now step 3. Right? I'm going to multiply row 1 times column 3. So 1 times 5 is, what will be 5? 0 times negative 3 will give us 0. So it'll be 5 plus 0 will give us 5. So that's first row, third column. Since we're done with the first row, right, times every column, now it's the second row that I need to multiply times every column. So row 2 times column 1, we'll repeat the process. 4 times 2 is 8. Negative 2 times 4 is negative 8, so it's going to give us 0. Then we continue to step 5. This is going to be 1, 0 for, again, we're going to multiply the second row times the second column. 4 times 0, negative 2 times negative 2 is going to be 0 plus 4, which will be 4. Finally, step 6, we're going to multiply the second row again times the third column. So 4 times 5 is 20. Negative 2 times negative 3 will give us positive 6. So it'll be 20 plus 6 will give us 26. So this is my solution. That's your matrix. Okay, now, hey guys, this is called the identity. The identity matrix is notated by the letter I for identity. For example, this is from section 1.1, that a real number 1 is the identity of element of the multiplication in real numbers. Why? Because 1 times any number will give us a number. For example, A times 1 is the same thing as 1 times A, which will give us A. In this section, the identity matrix, I, is the identity matrix. So for example, for a 1 by 1 matrix, it is 1. For a 2 by 2 will be 1, 0, 0, 1. For a 3 by 3 will be 1, 0, 0. You see, all the ones are diagonal, and the rest are zeros. So if it was a 4 by 4, it will be the same process. All the ones will be diagonals, and the rest will be zeros. That's called the identity matrix. Okay, now, say you have, if you multiply the matrix, right, matrix A times the identity. Let me show you why we get, for example, matrix A times the identity will give us matrix A. Here's the proof. This is matrix A, right? We're going to multiply times the identity. So again, right, we're going to multiply A times 1 and B times 0. Right? It's going to be A times 1 will give us A plus 0 will give us A. That goes on the first row, first column. Now step 2, I'm going to multiply the first row times the second column. A times 0 will give us, right? And then B times 1 will give us B. So 0 plus B will give us B. So that's my first row, second column. Since there's no more columns to multiply by, then step 3, I'm going to multiply the second row times the first column. See? So C times 1 will give us C, and D times 0 will give us 0. So C plus 0 will give us C. That's my second row, first column. And lastly, the fourth step, I'm going to multiply the second row times the second column. So BC times 0 and D times 1. It's going to give us 0 plus D, so the answer is D. So here, guys, let me go back real quick. I just proved it that when you multiply a matrix times its identity, you get the same matrix. Okay, now this is for this is the inverse matrices. I believe I only have like 2 more slides to go, guys. Okay, so thank you for staying and thank you for being patient. So for example, here it says, if you multiply A times the identity, A times the inverse will give you the identity. This is called the inverse matrix. So for example, I repeat, if you multiply A times its inverse, will give you the identity. So example 10, given matrix A and B as follows. Determine whether B is the inverse of A. So I'm going to multiply A times B. And if we get the identity, which will be 1, 0, 0, 1, that means both are inverse of each other. Okay? If it equals to 1, 0, 0, 1. Then B is the inverse of A because A times B is the identity. Okay, first of all, let me get the inverse here. This, right, is A times the identity. We're going to use the Gauss-Jordan method that we did in 6.2, right? So after I execute it, this is my inverse. Okay, but let me show you how it's done. Right? So this is the inverse, right? But how? Here's the work. I'm going to multiply, right? This has to be a 0 here. So I'm going to multiply negative 2 times row 1 and add it to row 2. Right, so here's my work. Negative 2 times 1, 4, 1, 0 will give us negative 2, negative 8, negative 2, and 0. I'm applying the same concept as I did on the slide that was explaining the Gauss-Jordan elimination method. Then I add it to row 2. Row 2 is 2, 6, 0, 1. So after I add it, right, it's going to give us 0, negative 2, and 1. You see, guys, I cannot simplify here, guys, because we have a 1 here. If we divide everything by negative 2 and multiply by 1/2, it's going to give us a fraction here, and we don't want that until the very end. So now, for the 4 is in row 1, there has to be a 0. So I'm going to multiply 2 times row 2 and add it to row 1. So again, since we use row 2, I'm going to keep row 2 the same. And here's my work. So 2 times row 2 will give us 0, negative 4, and 2. And row 1 will give us 1, 4, 1, 0. So after we add them, it should be 1, 0, negative 3, 2. So that is my new row 1. If you notice, this has to be a 1 here, right? For row 1, it's already okay because we have 1 0. But this has to be a 1. So I'm going to multiply row 2 by negative 1/2. So negative 1/2 times every term will give us 0, 1, and negative 1/2 times negative 2 will give us 1, and negative 1/2 times 1 will give us negative 1/2. You see, this is my inverse, guys. That's what I did earlier. That's how you do it. Now I'm going to show you one more way to get the inverse of our 2 by 2 matrix, and then we'll be done. There's a formula for that. Okay, here's a formula. It only works for a 2 by 2 matrix. So the inverse will be, this is called I believe, the determinant, right? So we're going to multiply A times D and subtract it from B times C. And then the A and the D switch places. You see they switch, and the B and the C, they switch signs. So find the inverse, right, of the one that we did earlier. Here we go. So it's going to be 1 times 6 on the denominator minus 4 times 2. And then on the matrix, we switch the 6 and the 1, right? They switch. And for the 4 and the negative 2, which is the B slot and the C slot, we change the signs. So here will be 6 minus 8 will give us negative 1/2. We multiply it times every element on the inverse here, guys. So it will be negative 1/2 times 6 will give us the 3. Negative 3, negative 1/2 times negative 4 will give us 2. Negative 1/2 times 2, negative 2 will give us 1. And finally, negative 1/2 times 1 will give us negative 1/2. That's how you find the inverse of a matrix by using the formula. Okay, now for a 3 by 3, guys, it's a little bit more challenging, guys, right? But I'm just going to go kind of quick, guys, and show you the steps because it's already time to go. Right? Use a Gauss-Jordan method from 6.2. And this should be the inverse. Okay? And let me see here. How? I'm not going to explain it, guys. You know what? Well, here are the steps, guys, okay? And I'm going to go slowly, guys, but I'm not going to explain it, guys, because it's time to go already. I don't want to take long like I did last week. Last week, I believe I went over like 45 minutes, and I don't want to do that anymore because the workshop should only be for an hour, and I already went over 17 minutes. But anyway, guys, you can follow this the similar way we did the other one. Okay, and here's the work that you do. Okay. If you want me to help you explain it, you can send me send me a message. I mean, send me an email at my email at aesasi@epc.edu, and I'll help you how to do this. Okay. But there's other work, guys. Okay. And at the end, right, you want all these to be ones, so you multiply by the reciprocal. And that's how you do this one. And again, thank you guys for staying over. And I apologize again for going over because they want me to only do an hour because that's the Friday Math Happy Hour is only an hour. But at times it's hard for me to stop because I want all my students to actually get the information. But I believe I give you enough info for you guys to be able to do the exam, which is this week. Okay. Thank you.
Thank you, Mr. Zassi. I'd also like to remind the people attending today that there's the Tejano Virtual Events playlist, and Mr. Zassi has done these types of inverses before. You're just going to click the link to go to the YouTube playlist and scroll through until you find inverses and matrices, and you can watch more examples of doing inverses. So I'd like to thank a minute to Mr. Zassi for presenting today and for everyone to coming today. And I'd like to invite you to next week. At 1 o'clock, we're going to have the El Paso Zoo Conservation Ambassador Program. And then for Happy Math Hour, we'll be going over basic matrix operations and inverses and matrices and determinants in Math 1314. And then in Math 1324, we'll be going over sets, concepts of probability, permutations, and combinations. Thank you all and have a wonderful weekend.